Okay. So first, couple comments about chapter 3 homework. So what's the problem? Has all the A, B, the double A, B?
Yeah, 3.4.
3.4 number 1. Okay, so because there's 2 sets of lettered parts. So just do part A on part A.
Right.
And you can interpret that however you want, and it'll still be valid. Because normally what he's done in these multi-part problems, he'd say do items 1, 2, and 3 on parts A, B, and C, but he didn't do that because he got sloppy. So that should resolve any ambiguity, I hope. Okay, so that's one thing. And then for, I think it's 3.1, okay, the problem with the Picard iterates. So when you get to a point where you compute a second derivative, and you're not giving much information about anything here, but so this is something that comes in the multivariable calculus. The multivariable chain rule is for when you have a vector field involved. So the derivative with respect to t of some vector field x that has as its inputs a vector value function of t. You'd actually use a chain rule, and it's very similar. So it's important that you recognize the similarity between what I'm about to write and just a plain old single variable chain rule from Cal 1. So first you take, it's how does the chain rule work? Derivative of the outer. Well, you take a derivative of a vector field. So that is actually a Jacobian matrix of your outer function. So that would be all the first partial derivatives of all the component functions with respect to all the variables. Evaluated at the inner function, f of t, times the derivative of the inner function. Well, that would just be f prime of t. So that's what you use to handle differentiating that whole expression with respect to t. And what's happening here, we're multiplying this by this. This is matrix vector multiplication. So a lot of things you learned in Cal 1, the way to generalize to multivariable calculus, it's much more easily seen what the relationship is when you think of things in terms of vectors and matrices, when you jump to higher variables. So multiplication that you know in a chain rule for single variable calculus just becomes matrix multiplication in multivariable. Similarly, okay, for instance, finding max and min. In one variable, you need the first derivative to be 0, and for minimum, the second derivative to be positive. In multivariable, you need the gradient to be 0 vector, and the second derivative is the Hessian matrix that has to be positive definite, or have positive eigenvalues. So it all generalizes in a natural way, seen through a lens of linear algebra, except when you teach multivariable calculus, you can't assume that students have had linear algebra, so you can't talk about any of that. Although most of you, well, I guess you're the only one who ever took multivariable calculus from me.
Yeah.
So
I didn't take it from me.
What?
I didn't take it from me.
Yeah, that's right, you did.
Yeah.
You did. She's the only one who
Oh,
did.
did. Oh, I
Yeah.
thought you said
But
didn't.
we did take it.
Right. Yes. So I went ahead and
I had the same teacher.
did all that linear algebra stuff anyway.
And,
Um,
oh yeah, that's right.
okay.
Yeah.
So hopefully that will
Great.
help you deal with that particular problem there. Okay. Now, today, we're moving forward into section 4.2, a section that is way too big to cover in one day, no matter what. Even without
So
spending
don't
more.
cover it in one day.
What?
Like, take 2 days to cover
I am actually. Yes. It's there in the schedule. I know I probably shouldn't cover 3.2 in one day either, but I couldn't help myself. I wasn't about to have Dr. Tian have all that. Bless you.
Nice.
Okay, so we'll just see how far we get with this section today, and then finish it up on Monday. Announcement. Okay. Maybe we need to move this anyway. Okay. There will be no class on Wednesday, October 21st, which is the Wednesday right before fall break. I'm flying out to California that evening, and I wouldn't be able to make it if I had class. I figured you guys want to be starting your fall break plans anyway. And also, following Wednesday, October 28th, that's when the Siam Linear Algebra meeting is going on. And not only will I be there, but half of you will be there. So I didn't see much point in having a substitute. I'm on the fence about the 26th. I will not be around. I will be in Atlanta during that time, even though the students won't be. And so I'm weighing whether to get a substitute or just not have class. We'll see.
Well, so.
Not have class.
I figured that would be at least one person's vote.
And you figured it would be by.
You'd be going there on Monday, but if we were going, we'd be going there on Tuesday.
Right.
So then how about 460, 560?
460, 560 will definitely not meet on Tuesday. Also weighing whether to get a sub. I probably will get a sub for that one. Just not sure.
But Dr. Harris will still take his class.
What?
Like,
Oh, yeah.
And then,
Yeah, so you're out of luck there.
but if we have homework,
And then
we'll be all right.
on Thursday that week, I will be back here in time to have 560.
And
Okay.
so are we gonna be back as well?
That's the plan, yes. That you guys should leave in the morning. And then with also gaining an hour from the time change, should be able to get back by 3:50.
We're gonna be together to discuss that. Yeah, we're
Yeah.
gonna meet to discuss it.
Are you going?
I don't know. I was so I can't.
Is the time change this weekend?
It kind of depends
Uh,
on.
What's the time change? No.
1 hour.
Oh, no, just the time
November.
change between he traveling here to Atlanta.
But
Oh,
It's
when is the?
November.
Oh, it's probably early November.
November.
Yeah.
Yes.
I have no idea.
but yeah.
I was gonna say.
Are
Hey,
we
could-
allowed to drive or?
Graduate students are allowed to drive a university vehicle. I'm trying to see if there's like a university vehicle available, like maybe a van or something. Except we're going to go in 2 shifts anyway, because Haley wants to go to class. As far as, I told Dr. Schroeder we had 10 students and we weren't going to let any more in. I wish you had mentioned this a little
Oh,
sooner.
it's fine. I've been to
I know,
around
yeah.
this one haven't been. Good.
Okay.
So it's fine.
Well,
I had that thing due on the 30th anyway.
yeah, well, still, that said, it'd be cool if you could go. But
Yeah. Well, it's-
How many people do you already have on board?
10.
Already?
Yes.
You're kind of in this.
Oh.
Yeah,
Oh,
yeah,
okay.
yeah, yeah.
Oh, okay.
That's what I said. Half the people are there. Anyway,
So are you the cashier kind of in that?
yes.
Okay, too bad.
Yeah.
Okay.
Yeah.
So,
I can put my name to drive.
Wow.
I love driving vans.
yeah. So,
No, I love driving vans.
Considering I have no idea what you guys are talking about.
the Siam Linear Algebra meeting. in
You're
Atlanta.
not part of Siam.
Atlanta.
Yeah, no, not.
Yeah, you're not even part of Siam.
Nope.
Okay. All right. Let's cover something.
Yay.
Not that I'd be all that broken up about falling behind, because some of the sections I got to cover later. Like, ooh.
Yeah, and so you just love to just like skip those.
Well,
Well, we have 2 days anyway.
I don't want to intentionally undermine myself, but it happens, and oh well. Okay. So 4.2, fundamental matrix. And the flow. Learn about the flow for nonlinear systems when Dr. Tian is teaching, but now we'll specialize that to linear systems, although I probably won't get that far today, especially at the rate we're going. Okay, so first is the definition of the fundamental matrix. Okay. fundamental matrix of a matrix A of t is a matrix G of t. Well, actually, I'll write it down here. So I'm typically going to use G of t to refer to a fundamental matrix. Why the book chooses the letter G, I have no idea. And it has columns. So I'll often write matrices this way in terms of columns. So gamma 1 of t, gamma 2t, and so forth, down to gamma n of t. So both of these matrices are n by n, and the entries are functions of t. These are columns. So it's often how I write matrices as a column partition, just write all the columns from left to right. Where each of these columns, gamma I, is a solution of an initial value problem involving A. So gamma I prime is equal to A of t times gamma I. And the initial value, gamma I of 0, is this vector EI. Now this is notation that comes up in linear algebra. Those of you who took my numerical linear algebra class already know this notation. But if you don't, I'll just define it now.
So the identity.
Identity matrix, yes. So the identity matrix, that's column E1, E2, up to En. So that's what I'm referring to is, that each column of G has as its initial value the corresponding column of identity. And if you're rusty on what the identity matrix looks like, so it's 1's down the diagonal and 0's everywhere else. So each column has a 1 in the jth position and 0's everywhere else. So I'm going to be using that notation fairly often, so it's important to get used to it. And if you will be taking like 561 next semester, it's going to come up there too. Okay. So a fundamental matrix, its columns are solutions, and actually makes it, the fundamental matrix is a handy device for describing all solutions of a particular system of ODEs for the whole vector space of possible initial conditions. Because your initial conditions can come from vector space Rn. So what we're doing is, by looking at the column of identity, this is the standard basis for Rn. So if we have a fundamental matrix, we can describe the solution of this initial value problem where we can have any initial condition. That's an E sub I there. Okay. Now, the thing is, unfortunately, the fundamental matrix is not always easy to compute. There are a lot of cases, even seemingly simple cases, where you cannot get an explicit formula for it. But we will look at some cases where you can. And certainly when A is a constant matrix, so independent of T, it can definitely be done there. That's actually something for the next section. Oh, okay. Thank you. All right. So for example, we have, here's our matrix for our system of ODEs. So, so what we want to do is fundamental matrix. It's going to have columns. I'll call them z1 of t, z2 of t, where z1 prime is equal to a z1 and z1 of 0 is the first column identity, 1, 0. And then similar for z2, that should be a prime. z2 prime is equal to at z2, and z2 of 0 is the second column identity, 0, 1. All right. Now, the way we're actually going to get these solutions is by using the fact that this system of two first-order ODEs is actually equivalent to a single second-order ODE. So what I can do is I can say let's x equal z1 and x prime. Okay, actually, I don't use that notation because it says those are my columns. All right. So if I have z prime is equal to az, so that's my system. So I want to write that out component by component. So I'll let z equal xy. So those are my components of z. So that means I have x prime is equal to 0 times x plus 1 times y. So x prime equals y. And then for my second equation, y prime is equal to this coefficient times x plus this coefficient times y. So this is the system written out in terms of components, but now what I can do is I'm going to differentiate the first equation. So that'll be x double prime equals y prime. So now I can just eliminate y altogether. I can combine this into a single ODE. X double prime plus 2 over t minus 1 squared, no, minus x prime plus 2 over, okay, this one's not squared, t minus 1 squared x is equal to 0. So now I get this single second order ODE that comes out of all this. So what we can do is go ahead and solve that, and then we have our solutions. Now, how do we solve this? Because we have variable coefficients. Those kind of ODEs are generally very difficult to solve. But here we have a nice special case. This is called a Cauchy-Euler equation. Now, a lot of first courses in DE, like 285, they ought to cover this, but I believe ours generally does not. And actually, Dr. Schroeder has said that 285 just doesn't cover enough, it needs to cover more. So we'll see what happens, we'll see how that goes. So in this case, we have a systematic approach to solving it. So what you do is, we assume that x, our solution x, is of this form. Because notice we have a t minus 1, powers of t minus 1 in the denominators here. So we let x equal t minus 1 to some power m. And we just got to figure out what are the possibilities for m. So what we can do is take this form of solution and plug it in here. And thankfully this is easy to differentiate just using power rule. So second derivative would be, okay, well, x prime is m times t minus 1 to the m minus 1, and x double prime is m times m minus 1, t minus 1 to the m minus 2. So now we can plug all of that into this equation, and we get m minus 1, t minus 1 to the m minus 2, minus 2 x prime, so that's m t minus 1 to the, I have m minus 1, but I have a t minus 1 in the denominator. So one factor cancels, and we get m minus 2 again. And then I have plus 2 t minus 1 again to the m minus 2, because I have t minus 1 to the m minus 2. We have t minus 1 squared in the denominator. And all of that is 0. So we have t minus 1 to the m minus 2 throughout all this. So let's just cancel that. And if we, so we get m squared minus m from here, minus 2m plus 2 is 0. So now we can just get a single quadratic equation. And sure enough, like any quadratic example, this factors nicely. So what we get is m minus 1 times m minus 2 is 0. So we have m is 1 or 2. So those are possible powers that work. And from there, we can describe a general solution. So that would be x is some constant a times t minus 1 plus another constant b t minus 1 squared. So that describes all possible solutions of this Cauchy-Euler equation, which would then be the first components of our solution z. Now we just have to find the appropriate a and b to satisfy our initial conditions. Okay, and actually I should write this as x of t, since it's definitely a function of t. Now, I got this news alert on my phone a few minutes ago that government averts possible shutdown. I've always found the term government shutdown rather amusing, because that would imply that at all other times government is actually functioning. Okay. Well, any questions about how this general solution was obtained? Okay. So now we just need to work with the initial conditions, and once we get those, then we will have our fundamental matrix. And if this is giving you the notion that getting the fundamental matrix is a real pain in the keister, you'd be right. It almost always is.
To find A and B.
Yeah.
And then
So, let's see, I think we're still for room. Okay. So in order to get z1 t, so that would be x of t, y of t. But keep in mind how x and y are related. Y is x prime. So our initial conditions will be, because we want this to be equal to 1, 0 when t is 0. So we need x of 0 is 1, and x prime of 0 is 0. So those are initial conditions to get our first column of our fundamental matrix. So x of 0 is a 0 minus 1 to the first, plus b 0 minus 1 squared. So that's going to be minus a plus b, and that needs to be 1. And then x prime of 0 is, okay, so that's just going to be a plus 2b times t minus 1, so that's going to be 0 minus 1. And if we simplify that, that's just a minus 2b, and that needs to be 0. So now we just need to solve this system of two linear equations in two unknowns. So what we can do is, if we go ahead and add the equations, well, the a's cancel out, and the b's combine, so we have b minus 2b. So minus b is equal to 1. So b is minus 1. And then the second equation says a is equal to 2b. So a is equal to minus 2. So z1 of t, our first column, is the so x of t, which is minus t minus 1 minus 2 t minus 1 squared. And then the derivative of that, so that's just going to be
You mean minus 2 t minus 1?
what?
You switched A and B.
Oh, yeah. Dang it. Okay. Minus 2 t minus 1 minus t minus 1 squared. And then the derivative of that is minus 2 t minus 1. And actually, all of this might as well be simplified. So that's going to be 1 minus t squared and minus 2t. Okay. So that is the first column of the fundamental matrix. Okay. Now, I won't go through all the details here because they're in the notes and time is fleeting. But for z2 of t, we have the conditional conditions x of 0 is 0 and x prime of 0 is 1. So we go through this whole process again. It's exactly the same thing, except on the right-hand side we have 0 and 1 instead of 1 and 0. So what happens in that case is you get a equals minus 1 and b is minus 1. So what happens in that case, you get z2 of t is t minus t squared, and then, ooh, typo in the notes. And then the second row is the derivative of that, so that would be 1 minus 2t. Okay. So now we have our columns of our fundamental matrix. So our conclusion is that the fundamental matrix is 1 minus t squared minus 2t, and then t minus t squared, 1 minus 2t. Now the only reason that the second row happened to be the derivative of the first is because this matrix came from taking a second order ODE and converting it to a system of first order ODEs. But you can have a more general first order system that doesn't relate to any higher order equation, and you would not have this relationship. But if you know that it comes from a higher order ODE, just convert to a system, then you will have that kind of thing. Okay. So in some cases, you can find a way to solve the system of ODEs directly, and then get your, and then you just apply the appropriate initial conditions, your columns of identity, and get the fundamental matrix that way. But we'll see, even when you have a just a 2x2 matrix, it can still be a pain. Okay. Some questions about this one?
why did we have x0 equals 1 and x prime equals 0 for
Oh, first column of identity,
right, 1, 0, and second column, right?
second column, yeah.
And you said it might not be the same way for everything.
Well, the thing is, you always have these kind of initial conditions.
Right.
It's just that this relationship of the second row being a derivative of first, doesn't always happen. This would only happen if your first order system can be described as one second order ODE.
But if that doesn't happen, what happens?
Well, but there's no particular relationship between these. It could be anything. Okay. All right. So now, this is the case for n equals 1, where we only have single first order single linear ODE. And that's something we know how to solve. In fact, I'll go ahead and ignore this term here. So in this case, it becomes particularly simple. So we'll assume that this is 0. So now we have this equation is separable. And we see this equation from time to time. The solution in this case is e to the integral of p times your initial value, y0, whatever that happens to be. Okay. So I'm going to let y0 be basically the identity matrix, but in this case it's just 1. So what that means is the fundamental matrix is, I'll just call it mu of t, is this exponential of this integral. So it's not really, now in this one-dimensional case, we can think of it as a fundamental function or a fundamental matrix. We know this from first-order linear equations as an integrating factor. This integrating factor is a solution of this initial value problem. So u prime, well, what is u prime? We have an exponential, so it's just going to be the exponential again, times the derivative of the exponent. What is the derivative of the exponent? Yeah, and p of t. So p of t times mu, and then the initial, what about the initial value? What is mu of 0?
The whole thing goes to 0, right?
What does?
The integral goes to
The integral goes to 0, and therefore you said
e to the 0 to 1.
yes. That's what you said, right? Okay, hey. Remember, my hearing sucks. Okay. So this is a problem in one dimension that the fundamental matrix solves. We can characterize it that way, that your fundamental matrix satisfies a system of ODEs where this is a matrix of your system, and then the initial condition is the identity matrix. So that's how it scales down in one dimension, but for any n, your fundamental matrix, G of t, satisfies this value problem. G prime of t is equal to A of t, which G is the fundamental matrix of, times G of t. And G is 0 is the identity matrix. In fact, many books use this as the definition of a fundamental matrix because, in fact, the proof is actually one of the least interesting proofs ever, so I'm not even going to do it. It's in the notes, but because how do we define G of t? It's a matrix full of solutions to this same system of ODEs. And what are the initial values? The columns of identity. So all the proof does is it just looks at this matrix equation one column at a time. So what we have here is, so each column, okay, I guess in an informal way I am doing the proof, but so each column's equation is gamma I prime is equal to A of t gamma I, and gamma I of 0 is the ith column of identity. So really the proof just works in terms of properties of matrix multiplication and what happens when you look at a matrix product one column at a time, and out pops this, but this is the definition of a fundamental matrix. So QED, and a very unsatisfying one at that. All right. But I find actually this notion of a fundamental matrix, I actually prefer to use this as the definition, since it's book didn't, as it's a lot easier to work with. Yeah.
Do you mean full form of QED?
Like how it's spelled out or whatever.
Yeah.
It's Latin, and I took Latin
Okay.
30 years ago.
Okay.
I know the E is erat, which was which was to be proven or something like that, like quad erat demonstratum or something like
Yeah,
that.
that's it. I just googled it.
Okay.
What is
Okay.
it?
Quad erat demonstratum.
I was gonna say, find what says Dr. Perry knows.
Oh yeah.
Oh yeah. So like which was to be proven or something like
I
that.
actually think he told us in
What?
class.
What?
Demonstratum.
They're
Which
translation.
is what had to be proven.
Yeah.
That's where you're one, left to right.
It's a small square.
Swish.
A small square.
That's what I'm gonna like.
Wingardium
Every proof.
Leviosa.
I'm like, alright,
One class.
Level
You
on
should
Harry
do
Potter.
that.
might.
You should teach with a one and be
Potter.
like, and we're done.
You don't care about
And your class is gonna
You
be
don't
like,
care about
They're just gonna sit there and just be like, why did we get this
what?
figured out?
Okay. No worries. What's wrong with that?
my
Well-
class does that all the time.
Well, I think what I should have done back when I proved that god awful existence of uniqueness theorem, I probably should have concluded that with a beta cadavra.
Yeah.
Cruciatus.
Yeah. That's what I start with. Yeah, you're writhing in pain for 75 minutes. Okay, but we only have 25 minutes left to suffer here. So now you do another example where we get the fundamental matrix. Now, here we have to use a very different approach than in the previous example. And this is going to seem very strange, but the reason I'm doing this example is it's a special case of one of the homework problems for this section. And so in the homework problem, you're doing the general case. All right, so we have x prime is equal to a of tx, where a of t is minus 1, 2t, minus 2t, minus 1. So what I'm going to do is I'm going to write out this system in full. So x1 prime, so so these are the components of x, is going to be minus x1 plus 2t x2, and then we have minus 2t x1 minus x2. Now I'm just going to rearrange these. So x1 prime plus x1, 2t x2, x2 prime plus x2 is minus 2t x1. Now, you've solved equations kind of like this, where you have something like this on the left side, and this invites using an integrating factor. So the coefficient of x1 here is 1. So the integrating factor, so actually for both of these equations, because they're both the same except x1 versus x2, they both can use an integrating factor, which is e to the integral of this coefficient here, which is 1. So it's just e to the t. So I'll go ahead and multiply through by this integrating factor. Okay. Now, the purpose of the integrating factor is to condense the left side into a differentiation of a product, because what we have here is the output of a product rule. So this left side condenses to e to the t x1, the whole thing prime. Because if you differentiate this using a product rule, you'll get exactly this. That's how the integrating factor is chosen.
What would you mean e to the t x2 for the first?
Here, yes.
And then,
Alright, dang it. Okay. And then e to the t x2 prime is minus 2t e to the t x1. Okay. So now notice that the only time you see an x1 in here is with an e to the t. And the only time you see an x2 is with an e to the t. So I'm going to introduce new variables. So I'm going to let u1 is e to the t x1, and u2 is e to the t x2. So in that case, the system simplifies to u1 prime is 2t u2, and u2 prime is minus 2t u1. So what's happening, and you'll do a more general version of this in the homework, is you find just the right integrating factors to condense the system to something simpler, where effectively what you have is only just one term here instead of two. Because so this is the system that we started with in the x's, but now down here each right-hand side is simpler. So that's really why we're doing this. Okay. So now, how do we go ahead and solve that? All right, so what we're going to do is we're going to assume the solution has a certain form. We're going to assume that u1 of t is equal to some function p of t squared. Right. And u2 is going to be the same function p prime of t squared. Now, this seems kind of arbitrary, but let's take a look at what happens here. If I differentiate this first equation, u1 prime is going to be p prime of t squared times 2t. But this p prime of t squared, that's u2. So it turns out by making this choice, the first equation in my system for u is automatically satisfied no matter how I choose p. And the reason for a t squared is the antiderivative of a 2t that we had in our equation. So that's the rationale for choosing that. So I didn't just pull t squared out of nowhere. Okay. Now, so now what happens is I'm going to go ahead and take this equation, differentiate it. Well, u2 prime is equal to derivative of this, p double prime of t squared times 2t. However, we already have something else for u2 prime from our system. So this is supposed to be equal to minus 2t u1. But u1 is equal to p of t squared. So now what I need to do is set these two equal to each other. So 2t p double prime of t squared is equal to minus 2t p of t squared. So the two t's cancel out. So p double prime is equal to minus p. So the equation for u1, as I mentioned, is satisfied no matter how we choose p. But by putting the two equations together, we now have an equation that characterizes p. Now, what's the solution to this? This is something that somebody in here should know. The second derivative causes a negation.
Sine?
Sine, yes, or?
Negative cosine? No.
Well, that would work too, but
Hyperbolic sign?
what?
Nothing.
No.
That doesn't change the sign.
Yeah, you're right.
So a general solution is actually a times cosine s plus b times sine s for any constants a and b. So it has something of that form. Okay, where I would use s equal t squared. Okay. So I'm going to make a couple choices here. So if I let p of s equal cosine s, so that means that u1 of t is cosine of t squared, and u2 is going to be p prime, so minus sine of t squared. Now, let's look at the initial values. I'll let t equal 0. So I get cosine of 0, which is 1, and then sine of 0, which is 0. So this is nice because the initial values are the first column of identity. So that's going to help me with getting the first column of my fundamental matrix. On the other hand, let's let p of s equal sine s. So u1 is sine of t squared, and u2 is a derivative, so cosine of t squared. And then if I look at the initial values,
You do get 0.
yes, so that works out nicely. Now, if I couldn't get it that nicely, I may have to play around with these constants a and b to see what values would work, but it turned out not to be necessary in this case. All right. Okay, now it's not u's that I want though. remember my first system had x1 and x2. I actually need those. All right. So for the first column, a fundamental matrix, so P is equal to cosine. So I get x1 t. So keep in mind how I define u. u1 is e to the t x1. So x1 is e to the minus t u1. So that's e to the minus t cosine of t squared. And then similarly, x2 of t is e to the minus t u2. So that's minus e to the minus t sine of t squared. So this gives me, so the initial values all work the same, so that e to the minus t isn't going to affect anything. So this is the first column of my fundamental matrix. And then for the second column, since P is equal to sine, I get x1 is e to the minus t sine of t squared, and x2 is e to the minus t cosine of t squared. The same initial conditions are satisfied. Really what I should have done is check the initial conditions at this level, the x's, not the u's, but it turns out to be harmless in this case. So now I can wrap up and say that my fundamental matrix is every function here has an e to the minus t, so I'll just factor it out. I have cosine of t squared minus sine of t squared, sine of t squared, cosine of t squared, and we're done. So a rather unusual approach, but this approach is actually useful for quite a few, at least in the homework you'll see how to do it for general 2x2 systems, that you can actually use this approach to first get a simpler system of your u's, and then solve that by finding a function p. You're always having to solve this equation in this form. P double prime is equal to something times p. Now, whether you can solve that is another matter. You might have trouble doing that, but in this case, it was easy. And then get your fundamental matrix. And then there's a later homework problem, which I have mercifully decided not to assign, that shows how you can do it for larger systems. So yes, the approach does generalize. It's just, it becomes more and more painful. And it really is about finding the right integrating factors.
This is not for the next one.
This is for chapter 4 homework. Yeah, so not for a while. Because it's actually going to take a while to finish that chapter. Ugh. Okay. Now, oh, not much. Okay. Very interesting.
What do we use this for?
What?
Like, what do we use this for?
Actually, where this is going is to be able to explicitly solve at least certain systems in general.
So can you use it like an integrating factor of the whole system?
Yeah.
Does that work that way?
Now, these are most useful for like small systems, although, as you'll see, in fact, actually from paper Hayview, sometimes these small systems are quite important that way. And most systems and applications are really PDEs, except you can decompose them into ODEs. So really, almost everything we see in this class are building blocks for hardware problems. And you have a lot of cases where we can't get explicit formulas, although they may still help as approximations as part of like a numerical method. In fact, really, the way I see analytical methods being used are they really help with building because the analytical methods usually work for the simplest problems, and their usefulness is limited in that sense. But then we can use them to help develop numerical methods for harder problems. Just like numerical methods for integrating anything are based on ways of exactly integrating polynomials. Okay. All right. Now, we're actually going to arrive eventually at a formula for explicitly solving systems in terms of a fundamental matrix. But we need, for this formula, I actually wrote down the formula last time, and we will arrive back at it again. But we need to know that the fundamental matrix, no matter where it came from, is invertible, because the formula, the solution formula, actually uses the inverse. So we need to have some assurance that it exists. Okay. Now, let's see if I can do this in 8 minutes. All right. So I'm going to let G of t, I can describe G of t in terms of its rows, R1, R2, and so forth. Okay. Now, G prime is equal to A times G. So what that would mean is, if I take a derivative of this, this is just R1 prime, R2 prime, is going to be, well actually I don't want to write out every row. I'm just going to write out a single row. So I'm going to look at this equation row by row. So what happens when you multiply these two matrices together and you're only looking at one row, row number I? What you're doing is, because you're going across the row and down each column, okay, so what you get is, all right. So it turns out to be a sum. So, like for instance, to get each element of this row, like element j, I'm going across the same row I and going down column j. But I want to get the entire row. So I'm going to get Aij Rj prime, or not prime, sorry, Rj of t. So what's happening is, this is row I of A of t, G of t. Okay. Now,
You do the ij entry of A
um,
times it
yeah.
with
right. Actually, what I'm going to do, shoot,
jth entry of G.
I'm going to do this element by element because this is not convincing. Well, believe me if you want, but I like to show it more explicitly. Okay, so if I let Ri of t, if I write it out component by component, Ri1, Ri2, Rin. So that means that Rik of t, the single entry of this row, is straight from a formula for matrix-matrix multiplication. It's Aij times Rjk of t. So this is really what we're looking at on an element by element level. But okay, and this is prime. So here I have R prime on this side, and then A times G on the right side. Okay, so this really comes straight from that. So this is one element of this matrix, and the right side is one element of this matrix. And this is formula for matrix multiplication. But I want to now group all of these together into one row. So if I take everything, if I look at what's happening here for all values of k, that takes me right back to this. Because here I'm looking at all elements of row I of a derivative. Here I'm looking at all elements of row j. So this is what I actually want to work with. So next what I want to do in the last 3 minutes, and this is going to get a bit linear algebra-y on you. Sorry. Not sorry. Okay. Oh. I've been. Someone tell me that I didn't move a computer. I need you guys to keep an eye out because I'm rushed and I'm gonna forget stuff. Can we all stay 5 minutes past?
Sure.
Yeah.
Okay. Really?
Yeah.
Okay, all right. Well, you have, yeah, mostly going over here. Okay, so what I'm supposed to show on the board for those, but one of you who's watching at home, is that I wrote G in terms of its rows, and using the fact that G prime is equal to AG, then, and actually, since I made a mess of this earlier, it's probably better if you weren't able to see it. So if I look at this one element at a time, one entry at a time, one entry of this matrix is here, the IK entry, and this is the IK entry of a product for which I use a formula for matrix multiplication. So this comes directly to this, and then I look at all the entries across a single row, and that brings me to here. And what I'm going to use this to look at how the determinant of G of t behaves. And now that I have this freshly erased board, I can take this back over here and try to get this crap right. Sorry, I'm over this week already. Too bad it's only Wednesday. Okay, so Ri prime is equal to sum Aij Rj. So that's the relationship that I copied from a previous board that we're working with. So now the derivative with respect to t of the determinant of G of t, okay, is so that's the determinant of R1, R2 down to Rn. Okay. Again, because the R's are the rows of a matrix. Now, so what happens is, and you're going to have to take this on faith because there had no time. When you take the derivative of a determinant, it has a product rule-like relationship. So you end up getting a sum of, so the derivative is the sum of determinants. Okay, if I'm not careful, I'm going to run out of room. So R1, Ri prime. So what happens is, okay, in each term of this sum, row I, and only row I gets differentiated. All the other rows get left alone. So now, to save space, I did this in the notes too, I'm going to write the rows horizontally because otherwise everything will be too condensed. So I can replace that derivative with that expression there, the sum over j, this is the sum over j, okay, all the way to Rn. So I'll just, so the one row that gets differentiated, I replace it with this. Okay. now, a determinant is a multilinear function. So I can actually pull this sum out, and I can pull these constants aij out. Okay. So now I have a sum aij. I'm sorry, these are not constants or functions of t. That's okay, it still works. Times the determinant of R1, Rj, Rn. Now, here's what happened. Ri prime is now occupied by Rj. Now, what happens when a matrix has two rows that are identical, and you take the determinant? So, two rows are the same. What happens to the determinant? It's what? The matrix is not invertible, therefore the determinant is 0. So all of these terms are going to drop out, except when I equals j. So now this is a single sum, aii, times the determinant of R1 to Rn. All the rows are different now. But all the rows, R1 to Rn, forgetting my vector symbols, that's g of t. So now I get the derivative determinant of g of t is the trace of a of t times the determinant. And the trace is the sum of all the diagonal entries. That's how the trace is defined. Okay. So, but the thing is, the derivative is equal to itself times this trace. Well, that's an ODE that can be solved. So the determinant is equal to the exponential of the integral of the trace. Times the determinant of g of 0. But what is g of 0?
The identity.
Identity matrix. So the determinant of g of 0 is just 1. So this is it. This is the formula for the determinant. And this has a name. It is called Liouville's formula. Not Louisville, Liouville. Liouville's had several things named after him, actually, from differential equations, PDEs, and complex analysis. Okay. Now, because this is an exponential of something, it doesn't matter what it is, the point is exponential, it is never 0. So, so Liouville's formula, what we really need from it is we know that g of t, no matter what matrix A it came from, is invertible. So unless you have a finite matrix whose trace is minus infinity, as in that could never happen, we have an invertible fundamental matrix. And that's going to be very important for what I do not have time for today. We'll have to wait till Monday to come up with an explicit formula for the solution of a first order system of ODEs. So thank you for sticking around. And we will try to finish this section on Monday. And by Monday, I also hope to get your first homework graded back to you.
You could just give us all A's.
Actually, so far they are all A's, but just haven't got to a few of them yet. Okay.
Homework 1?